the positive x-axis of this one, and let's start the clocks when the oranges coincide. And in that case, we discovered that the relationship between the two coordinate systems was that x prime would be gamma x minus dt, and t prime would be gamma t minus vx over c squared. And the other two would not change. And the only difference between what this fellow sees and this fellow sees is that this guy sees this one moving with speed v in the positive direction. This one sees s moving with speed v in the negative direction. And so the inverse of these was x was gamma x prime plus dt prime, and t was gamma t prime plus dx prime over c squared. And then, using those, we had asked the question, suppose you look at a clock in S prime from S. How does a time interval, the time it takes for 1 second to pass in S prime, coincide with the time that you see? And what we discovered was that delta t was equal to gamma times delta t prime, provided you looked at one particular clock. It would appear to run slow, so that 1 second in the S prime system would be like 5 seconds in your system. On the other hand, if we looked at the clock that was directly overhead, which would mean a different clock each instant because S prime was moving, then you got the reverse answer. That those clocks appear to run more slowly. All right? Then we looked at lengths. And in that case, we got that the lengths appear to shorten. All right? Now, everyone's okay to there? I mean, not okay in the sense that it felt good, but you understood the logic of how we got that. The critical thing was to be very careful to define accurately what exactly you were measuring, how you were measuring it. Now, to see that we understood that, we're going to look at some of the famous relativity paradoxes. There are none, of course. They just appear that way due to a misunderstanding, which we're going to try and fix. So the situation I want to look at is two rocket ships. Each have identical length as measured by their crews. So we have rocket ship A, which has a length L0, as measured by its crew. And we have rocket ship B, which has a length L0, as measured by its crew. And the two ships pass one another very, very close, so that the distance between them is negligible. Now A is militaristic and has a tail gunner. And the pilot of A instructs his gunner to fire when the tail of B coincides with the nose of A. Tail of B coincides with nose of A. Gunner is to fire. Now the gunner considers this and thinks, this is very strange. I'm firing too soon, because as A sees the situation, B is moving and therefore appears to have a shorter length than the length that the measurements made in B would indicate. So that A sees this, L0 divided by gamma, L0, so he's going to miss. On the other hand, what does B see? B, looking at this, sees A as having shrunk. And therefore, since A has shrunk, B would appear to see, and it's a hit. Now, either B blows up or it doesn't. Now, which is it? Why? So we work the problem from the standpoint of each observer, and we come to opposite conclusions. But as we said, events simply are. Doesn't matter who looks at them. So either B is going to blow up or it isn't. So, which is it? How many are betting on B surviving? How many are betting on B not surviving? All right. Well, now, let's start. I'm going to work it out very carefully from the equations in a second, but let's look at the physics for a minute. How many events are there here? 2. The nose of A coincides with the tail of B. Event 1. The gunner fires. Event 2. Now, remember I mentioned earlier that we're going to have trouble with simultaneity. 2 events that are simultaneous for one observer are never simultaneous for another observer moving with respect to the first one. Now, A is the ship with the gun. The gunner and the coincidence of nose and tail coincide in A. Will they coincide in B? No. And what's going to happen when you work this out is that the bottom picture for B is not going to be quite right. Because this assumes that this event and that event are simultaneous. But if they were here, they can't be here. So what really happens is this. And as B sees it, the gunner in A fired too soon. A shrank all right, but the gunner in A disobeyed instructions and fired too soon. Now, let's work this out on the equations. Physically, that's going to be the situation. Now let's work it out from the equations. So what we have to do is set up coordinate systems. So first we'll have coordinate system S. That'll be the rocket ship. So let's just label it coordinate system A. And let's do it this way. So the origin is at the tail of A. So this is the tail of A, X tail A. And this is the nose of A, X nose A. And now, for B, let's do it like this. Here's B. We're interested in the nose of B coinciding with the tail of A. So let's do it like this. So here is X tail B.
Put your A should.
I got these backwards. This is nose. This is tail. And this is nose. Yeah, thank you. And then this one is, so that's X tail of B, and this is X nose B. Right. Okay. Now, what are the transformation relations? Well, in this situation, is moving down the negative, in the negative x direction, as seen from S, because the ships are approaching. So for us, the transformation equations, let's call this is the prime system. All we have to do is change the sign of v. So that we get x prime is gamma x plus dt. T prime is gamma, we'll change the sign of v, t plus vx over c squared. And then going the other way, gamma x prime minus v t prime, and t gamma t minus vx prime over c squared. Okay, so those are going to be the relations between the values that the two people see. Now, what do we know? The quantities that we're going to be interested in are the nose of A, the tail of A, the nose of B, the tail of B, and times. Now, for the nose of A, by the way we set up the coordinate system, in the A system, or the unprimed system, the nose is at the origin. So that is 0. The tail is at minus L0, because the length of the ship, as seen by the crew, that's A, is L0. And therefore, the tail of A is L0 to the left of the nose, and therefore in the minus x direction, so it's minus L0. Now, the nose of B, well, the nose of B is at minus L0 in the prime system, and the tail of B is at the origin, which is 0. Everybody on board so far? Okay. Now, what do we know about the times? We know that the time for the tail of A, when the event occurs, is 0, because in the A system, the gunner was to fire when the origin and tail coincided, but that's where the clocks start, because by our transformation equations, the clock starts when the origins coincide. So xTA equals 0, and TA, and T nose A equals 0. Because the gunner fires when the clocks in the A system, the unprimed system, both read 0. Okay? Now over here, we will have T prime, tail A, T prime, nose A. They do not necessarily equal 0. Okay? So now, let's see what we can do here. First of all, let's analyze it from the standpoint of A. And so from the standpoint of A, what we care about is where is the nose of B? If the nose of B is further to the left than the tail gunner, I'm going to hit it. If it's to the right of the tail gunner, I'm going to miss. So what I need to know is where is the nose of B? So X nose B. Okay? So we go up here. X nose B should be gamma times X nose B prime minus V T nose B prime. Alright? Now, X nose B prime, that we know, is minus L0 minus V T nose B prime. But we then need T knows B prime. So we go here. T knows B prime is equal to gamma T knows B plus B x knows B divided by C squared. Everybody following so far?
What was that middle step where it doesn't have what it's equal to?
I'm just substituting what I know. I know that x knows B prime is minus L0. Now, I know something else. I know that this is equal to 0 because this is the time when the nose of B coincided with the tail of A. That's when everything is occurring over here. So I can write right here, T nose B is equal to 0. And therefore, this becomes gamma B x nose B divided by C squared. So I put that back here, and I get x nose B at the instant the gun is fired is gamma times minus L0 minus V, and I put that in, gamma B over C squared x nose B. So now I bring this over to this side, and I get x nose B times 1. Gamma B squared over C squared, makes that a plus, gamma B squared over C squared equals minus gamma L0. But gamma is here. So I have x nose B times 1 plus B squared over C squared multiplied by gamma squared, there's two gammas here, so that's a gamma squared. This one times this one. And gamma squared is 1 over 1 minus V squared over C squared is equal to minus gamma L0. But this put over a common denominator is 1 minus this plus this. That's just 1 over this. But 1 over that is gamma squared. So you get gamma squared x nose B is equal to minus gamma L0. And therefore, x nose B is equal to minus L0 divided by gamma. Which is exactly what we thought the gunner in the people in A would see. Okay? Everybody followed that? All right, now let's look at it from the standpoint of B. So now, what we need to know, what B is concerned with, is where is the tail of A? Because her fate depends on where that gunner is when he fires. So, we need to find x tail of A as seen from B. All right? Well, we know how to do that. That's up here. It's gamma times x tail A plus B, x tail A plus B times T tail A. But now we know what each of these things is. X tail of A is minus L0. And the T for the tail of A when the gun is fired is 0. Because they started the clocks when they coincided, and that's when the gun fires. And so, the tail of A, as seen from B, is at minus gamma L0. And therefore, she's safe. Because her location, the nose of her ship, is at minus L0. The gun is further to the left than that. It's at minus gamma L0. How did it happen? Well, to see that, let's find the time at which the gunner fired, as seen from here. So, T prime of tail. Well, we know how to do that. That's our equation up here. It is gamma times T, tail A, plus B xTA over C squared. Now, the gunner fired as seen in the A system at 0. xTA is minus L0. And therefore, minus gamma B L0 over C squared. So that as the pilot of B sees it, the tail gunner disobeyed and fired too soon. So we get the picture that we ended up with up here. A has indeed shrunk, as seen by B, but the events were not simultaneous. The gunner fired too soon. Making sense to everybody? We can go one step further and see the relationship between the distance of miss, as seen by the two observers. You can do that, and if you do it, you'll find that the amount by which they miss is gamma minus 1 times L0 in one system, and that divided by gamma in the other. Because the lengths will shrink. So there's no paradox. There appeared to be one because we made the mistake of thinking that the events were simultaneous in both systems. Now there are semi-infinite number of such paradoxes, and they all revolve around the idea of simultaneity. That's what went wrong with our sphere with two centers. There were two events. Light reaches one side of the sphere, light reaches the other. Those are simultaneous in one system, they were not in the other. And that's why it appeared to have two spheres, two centers. Okay, are we making sense here?
Can you explain with the T with the positions, the different T's?
There's a clock, you remember, at every position on the wall in the system. And so when I write T nose of A, I mean the clock located at the nose of A in the A system. When I write that in the prime system, it is looking at the clock that's at the nose of A, but looking at it from the prime system. So those subscripts simply refer to the fact there's clocks on the wall. Okay. Now, I want to go back and do this and derive all of this stuff from a different viewpoint. And the different viewpoint is going to be geometric. And in order to do that, we need to introduce a couple of new ideas. The first thing I want to do is to use the fact that we've decided that the geometry, since it links time and distance, we can no longer think of a three-dimensional universe where there's space here, and then sitting off by his side with no connection is time. Rather, they're put together. And so we now have to think of a four-dimensional universe that contains three space dimensions and a time dimension. Now, it won't be quite the same kind of four-dimensional universe as we had with three dimensions when you come to consider the Pythagorean theorem. But we'll do that in a little bit. For right now, we want to make this monumental step of recognizing time as just another dimension in our space-time. Now, and then as you think of it that way, then you realize why we got this mix. Of course, this is just saying the same thing backwards. And that is if you had two coordinate systems, x, y, x prime, y prime, if you rotate the axes, then what was pure x in one becomes a mix of x and y in the other. What was pure space in one becomes a mixture of space and time in the other. Now, I want to picture then, since all the space dimensions are basically the same, it's just a question of where you try to draw the axis, but they are in principle, they can be different from the time one. So I'm going from henceforth, instead of trying to sketch four dimensions, or even three dimensions, I'm only going to sketch two. One is time, and one is space. Because those are the two that are going to matter. The other, the y and the z, I could equally well have called x. So they aren't fundamentally different. So I'm going to look at axes that look like this. This is x. Now, it will be very convenient to have the same dimensions on each axis. So instead of plotting t as a vertical axis, I'm going to use ct. And ct will have dimensions of length. And it's just a scale factor. So this axis is going to be ct. And now, the first thing I want to do is ask the question, in that picture, what would a light beam look like? What would be the path of a light beam? Well, the light beam is going to have always the velocity c, and therefore the distance it goes in time t is going to be ct. So that means the path of a light beam must be lines on this at 45 degrees. So that the distance you go at the x-axis is always the same as the distance you go at the t-axis. So that the light is traveling with speed c. So, light beams will move like this. So this will be the path of a light beam. Everybody see that? If I had drawn one more dimension in space, that would have become a cone at 45 degrees. If I had drawn all three, it would have been a sphere, expanding in ct. I'm just going to draw it this way. Now, material particles, things with mass, we decided could only travel speed c or less. And the reason was that gamma, which was 1 minus v squared over c squared, became imaginary if v was greater than c. So you couldn't physically have a situation where v was bigger than c. So, if you're always going to travel with speed less than c, what are the possible paths on this diagram? Well, they always go through the origin, that's where we started. But they must move so that they always go forward in time, but they have to stay inside this cone. Because ever to get outside the cone would require you to be traveling faster than the speed of light. And to get to here, you could have followed any path you want, provided you stayed inside the cone. And never had a slope here that got you outside the cone. So, this region inside the light cone is the places you can get to. Right? You can't travel faster than the c, so you can't get outside that cone. So that we could call this region of space-time your future. And this region of space-time is the region you could have come from. You can't come from over here because you'd have had to travel faster than the speed of light to get to there. This is a region you can neither have come from nor go to. And so we're going to call this elsewhere. And same thing over here. In other words, because the speed of light is finite, the space-time has now got 3 regions in it instead of 2. If the speed of light were infinite, you could have come from anywhere, you could go from anywhere, there would only be the future and the past. But in relativity, there's the future, the past, and elsewhere, which you can have no connection with. You can't have come from there, you can't get there. It's outside your realm of possible experience. A totally new concept. It did not occur in classical ideas. Yes?
So, is elsewhere necessarily outside of the universe? Or
No, it's outside your possible realm of experience. It is not outside the universe, but it's outside anything you can experience or have experienced.
So, meaning something, in putting it into English, something in the past occurred that is completely blocked out the possibility of something else happening in the future?
No. What it means in concrete terms is this. You're watching through a big telescope astronauts on the moon, and they're collecting rocks and things. And you observe that there's a rock rolling off the top of a crater that they're at the base of. And you see that that rock is going to hit them. It's going to hit them, let's say, in half a second. And it takes 1 second for a signal to reach the moon from the Earth. Those numbers aren't right, but just take them for that. Is it possible for you to do anything to influence the effect? No. Because by the time your signal had gotten there, the astronaut's already crushed. That's elsewhere. You can have no impact on the regions that would have required faster than the speed of light to get there. It's in the universe. The astronaut gets crushed. So it's there. It's just that it's outside your realm of experience. Yes?
So what about the spooky action at a distance?
Well, this means the action at a distance can't be right. And so it forces a fundamental change in Newtonian physics. And we're going to talk about that. Now, the path that something follows in this space-time diagram is called a world line. That is the path, just the trajectory that the object follows. Only now it's a trajectory in this space-time rather than just in space. So that this is a world. Okay, now, with those definitions behind us, we're now going to proceed to derive all of the effects we've been talking about from purely geometric considerations. This is CT, this is X. Now, let's consider an observer, another system, S prime, moving with speed v in the usual fashion down the positive x-axis. What will the trajectory of the origin look like in this diagram? This is a diagram from the standpoint of S. Now, the new system S prime is moving down the positive x-axis with speed v, which is a constant. That means it's just a trajectory in this plane where this angle, theta, has the tangent of theta equal to this distance divided by this distance. This distance is the distance x that you went, which is v times t, because you're traveling with speed v, and time t has elapsed, divided by this, which is ct, and therefore is v over c, which we traditionally give the symbol beta. So, this is the axis ct prime, because that is the line along which the origin is moving in the time direction. Now, in the S prime system, what does the speed of light do? Nothing. It travels just the same as it did before. And that means that the path in the prime system has to be a straight line equidistant between the time axis and the x-axis. Right? Otherwise, it would not be traveling with speed c. And that means that the x prime axis must be inclined upward at the same angle as this one was inclined that way, so that the path of a light ray is always the same. Because that's got to be the same in either coordinate system. Got the picture? Okay. Now, with that as the general shape of these two systems, down here to just the picture with the CT prime. And I want to consider launching a light beam from this location, CTA, over toward this observer. Now, what will that light beam look like? It will travel at 45 degrees, so it will come up here. It hits a mirror at this point, and it bounces back like that. Okay? Always traveling at 45 degree angles, because CT must equal X for the light ray. Now let's suppose it hits over here at a position we'll call CTA prime. And it bounces back to here, arriving here at time CTB. Okay, now the origins coincided here. The time interval between here and here, CTA, and the time interval between here and here, because the space-time is going to be uniform, so everything has to be linear. So whatever this is, it must be just some constant times that, so that it will be linear. So let's call that constant kappa. So we get kappa times CTA. All right? Now, is there any fundamental difference from one observer to the other? No. They're all equivalent. And therefore, this time interval from here to here must just be that same constant kappa times this time interval. Because this compared to this is the same physical phenomenon as this compared to this. Here the light ray originated on this one. Here it originated on this one. But the time to go from here to here compared to this must be the same relation as the time to go from here to here compared to that. They're the same situation. So this must be kappa times kappa CTA. Okay with everybody? See what we're doing here. We're simply saying that whatever the connection between them is, it's going to be linear. Otherwise, the laws of nature would depend on where you were. There is no difference fundamentally between observer A and observer B. One is moving relative to the other, same velocities. So, comparing this to this, with this being the source, is the same as comparing this to this, with this being the source. And so the connection is just a factor kappa in either case.
Professor, can we put this drawing in physical terms again too, so we have like a laser push button and
Yes.
a little truck that's going in speed?
What this consists of is the observer in A has a laser. There's a mirror at the origin of the prime system. Okay? After a certain time interval, I pick my laser here, aimed at the mirror here, it hits the mirror, bounces off the mirror, and returns to me up here.
When the mirror is moving very fast?
The mirror is moving because this system is moving down my positive x-axis with speed v. All right? Now, what is this distance? Well, how would you measure the distance from here to there when the only thing you're sure of is the speed of light? You know the speed of light is you know what that is. That's the only thing you're absolutely confident of. The world is really getting shaken up here. So, what do you know? If I send this to there, it hits there and bounces back, and it takes the time t to return to me, how far was it to there? It would be the time that it took to return to me, multiplied by c, divided by 2. Half the time going out, half the time going back. Right? So, this distance, let's call it L, is the time it took to return, to go on and return, which is CTB minus CTA divided by 2. But I know what this is, because this guy is traveling with speed v, and he does it for a certain length of time. What length of time is that? Well, it's this time. And this time is the average between those. So it is CTB plus CTA divided by 2. So I must have this is equal to that. Everybody following? But I know what CTB is. It is kappa squared times CTA. So what I have is kappa squared minus 1 times CTA divided by 2 is equal to B times kappa plus 1 CTA divided by 2. No, kappa squared. CTB is kappa squared of CTA. Okay with everybody? All right. So I can write out the CTAs, and we've got a unit error here, so let's see. This is correct. This is not correct. I have to divide by C. Because the distance traveled is the velocity times the time. Since I've got that multiplied by C, I have to divide by a C also. So I have C. Okay, so now I can solve for kappa. And therefore I can find what that relationship between those two time intervals is. And so I can divide out the 2's. And so I have kappa squared times 1. I bring this one over here. B over C is what we call beta. So 1 minus beta. And now I bring this one over here. And so I get beta plus 1. So kappa is the square root of 1 plus beta over 1 minus beta. So that is the relationship between, that's the kappa that relates times on one to times on the other. Everybody following so far?
Where did beta come from? Where did beta come from?
That was redefined to be B over C. Just as a traditional notation. Okay, now that we've got this, we can determine the time intervals as seen by the two observers looking at one clock, namely the clock at the origin. So we can now, because we know the kappas, we can compare the time interval as seen on the S prime, where the clock is located, compared to the time interval that I have. Now, my time interval is from here to here. The time interval with the clock, moving clock, is from here to here. Now, what is this time interval? Well, that's CTB plus CTA divided by 2. So, delta T, as I see it, is CTA plus CTB divided by 2. But that is kappa squared plus 1 times CTA divided by 2. The time interval on this clock clock I'm looking at is CTA times kappa. So this is delta t. This is delta t prime. CTA times kappa. So my time interval, delta t, over the time interval for the clock that's I'm looking at is the CTAs cancel out, and I get kappa squared plus 1 divided by twice kappa. Now, kappa squared is 1 plus beta over 1 minus beta. It's the square root. 1 plus beta, 1 minus beta. Okay? Now, put this over a common denominator, and you get 1 plus beta plus 1 minus beta is 2 over 1 minus beta, divided by 2, 1 plus beta, 1 minus beta square root. The 2's cancel out. Bring that downstairs, put it inside the square root, and you get 1 over 1 minus beta squared to the 1/2, which is gamma. And that's our time dilation. That the time interval I measure will be gamma times the time interval shown on the clock that I'm looking at. Okay, now next time, we'll look at length contraction. And we'll look at the length as measured in the tube. And then we'll be able to take those two results, make this an appropriate diagram there in which we look at both axes and get the Lorentz transformations. And we do it entirely just geometrically this way. Okay, have a great day.